Alright, so I think today might be a good idea to talk about a really easy way to balance combustion reactions. So let's say that we have a fluid reaction. Let's say that C3H6O acetone. Actually, this has isomers, but we'll say this is acetone plus O2. Right. So what does that form? We're burning up some acetone, C3H6O. So we're burning it up. We're gonna form carbon dioxide. Right. Carbon dioxide and a little water, right? A little water. And this is complete combustion, right? Incomplete combustion, we'll get weird things like carbon monoxide and carbon, soot, whatever, and stuff like that. But we're focusing on complete combustion. States of matter, they're irrelevant because I'm just talking about balancing. But basically, 99% of the time, the pain that comes from balancing comes from these oxygens, right? Balancing the oxygens. Because see, all the carbon goes into carbon dioxide, that's nice. All the hydrogen goes into water, so that's cool. But all the oxygen is split kind of between the carbon dioxide and hydrogen. Carbon dioxide and water. So I think, so the first thing, right? The thing we want to focus on is first balancing the carbons, balancing the hydrogens, worry about the oxygens later, right? So let's see here. On this side, we have three carbons, right? Here we have one carbon, holding the CO2. We'll put a 3 right here. Put 3 CO2. Right? I don't care about the oxygens, we'll worry about that later. So 6 hydrogens here. We have 2 hydrogens here. So if we put a 3 right here, right? Put a 3, we get 3 times 2, 6. 6, that's pretty cool. Alright, that's good. So we balance the carbons, we balance the hydrogens, the oxygens though. The oxygens are scary. So let's see how many oxygens we have on this side. So see, 3 times 2 is 6, you have 6 oxygens, plus 3 times 1, this is 3. So we have 9 oxygens on this side. But on this side, so on the acetone, we only have 1 oxygen. So the name of the game here, I guess, is that we don't need to modify the coefficient of our fuel, right? Because if we do that, it's gonna make things harder. So I mean, the acetone, right, they took care of only 1 oxygen. So we need this O2 to take care of the other 8 oxygens. So we can easily make it do that by putting a 4 right here, right? We're putting a 4 O2 because 4 times 2 is 8, right? So that's pretty cool. That's and really our entire thing is balanced because 3 carbons right here, 6 hydrogens, 3 times 2 is 6. We got that. 9. So 3 times 2 is 6 plus 3 is now 9 oxygens here. 1 plus 4 times 2, 1 plus 8, 9 oxygens here. Our thing is balanced. Now let's suppose here that this was I don't know. Suppose an O2. Suppose this was a C3H6O2. Whether this compound exists or not, that's irrelevant. This is just for an example. But suppose it does exist. So this thing would have taken care that this whatever this compound would be if it exists. It would have taken care of 2 oxygens, right? 2 out of our 9. So this would be our O2 would be left to deal with 7 oxygens. Now this 4 is not going to work. But what we can do is instead of having a 4, we can just put we can put 7 halves, right? Because 7 halves times 2, that's just 7, right? So I mean that would have taken care of it. But you might be thinking that it doesn't make sense to have like 7 halves of oxygen O2 react with one of these C3H6O2s if it exists. It doesn't make sense to have 7 halves of like a reactant. And yes, it does not make sense to have 7 halves of a reactant, but the fact of the matter is we don't really care. Because if we're in stoichiometry, we're doing stoichiometry, it doesn't matter if we're dividing by, it doesn't matter if we're doing 7 divided by 2 or 7 halves divided by 1. The math is going to work out to be the same. So, I mean, that's pretty cool, really. Nice method for balancing combustion reactions, crazy ones. Easier than what my teacher told me, at least. So, follow for more things like this.